In today's lesson 3.4, proofs with perpendicular lines, you'll learn how to find the distance from a point to a line. We're supposed to construct perpendicular lines, but we'll wait till Friday before we do that, and we'll solve real-life problems. First, let's talk about the distance from a point to a line. So if you take a line and you have some point somewhere, and you want to measure the distance between that point and the line, you wouldn't measure from that point just anywhere onto that line. Just like if you were trying to measure the distance from the ceiling to the floor, you wouldn't measure at a slant, use a slanted line to measure from the ceiling to the floor. You would make sure it's perpendicular. Like you would probably go to the corner or go to one of the walls and measure from the top to the bottom using the wall as a guide to make sure that that line is perpendicular. So the way you measure the distance between two things would be the perpendicular distance between those two things. So if you have a figure and you're trying to find the distance from some point on that figure to maybe the side of that figure, which would be a line or a segment, you would have to make sure that whatever you're measuring is perpendicular. Next, perpendicular bisector is, if you'll remember, we've already talked about angle bisectors. That's when you have something that cuts an angle into two congruent angles, like a ray or a line or a segment even. But let's think about a perpendicular bisector. With a perpendicular bisector, you have two things going on at once. Something's perpendicular and something is bisected. So if you take and draw a segment, the perpendicular bisector to that segment would be a ray, a line, or a segment that cuts through this segment at a perpendicular angle. Right angle, perpendicularly. Which means that would be 90 degrees. And at the same time, it is cutting that segment into two congruent segments. So it's perpendicular and it bisects that segment. We will be constructing these on Friday. So, all right, what's next? Finding the distance from a point to a line. So here's a figure. It's in your book. You might want to turn to your, what page? Let's see, page 152. It's number 4. It says find the distance from point A to XZ. So from point A to XZ, we have 3 segments drawn. We have this segment, we have this segment, and we have this segment. We have to choose the correct segment to take the measure of so that we know the distance from point A to segment XZ, which is this segment. So what you want to do is pick the segment that's perpendicular to that. So from A to Z is the perpendicular distance from point A to segment XZ. So to find the distance between 2 points on a graph, remember we have the distance formula. You can use the distance formula just make sure you use it correctly if you're going to use it, or you can use my formula, or well, it's not a formula, it's a shortcut. The distance from A to XZ the number you put here would be the x coordinates, how far apart they are on a number line. So from 3 to 4, that distance is 1. Think of distance from 3 to 4. From 3 to -1 for your y's would be 4. The distance on a number line from 3 to -1 is 4. So that's just a quicker way. That way you're not plugging in 4 numbers and having to pay attention to your signs and then simplifying and squaring and all that. So now we just square 1 and square 4, and the answer is the square root of 17. That's the answer that I like, is the square root of 17. The book's going to give you a rounded answer, and you can estimate if you want to. That's fine, especially if you're trying to check your answer, make sure you did it correctly. But as long as your radical is reduced, if it's reducible, I like the radical answer. So this would be an acceptable answer for me. Just to review quickly how to reduce radicals in case you have one that you need to reduce. Let's say you have the square root of 10. Well, for some reason, some people want to tell me that's 2 times the square root of 5, just because 2 and 5 are factors of 10. There are no perfect square factors of 10. So the square root of 10 is reduced. That's the answer. If you get that as an answer, it's not reducible. But if you get the square root of 12, 12 has a perfect square factor of 4. So the square root of 12 can be written as the square root of 4 times 3. Then you can break that up, the square root of 4 times the square root of 3, so that you see the square root of 4 is 2, and then 3 is left under the radical. The only way something can come out of the radical is if you can take the square root of it. So if you have factors under the radical and it's not a perfect square factor, or you can't come up with a perfect square factor, it can't come out. In order to come out of the radical, it has to change. So saying that 2 times the square root of 5 is the reduced form of the square root of 10 doesn't even make sense. So make sure you know what you're doing when you reduce. You have to have a perfect square factor like this. And your perfect square factors are 4, 9, 16, 25, 36, 49. You get the point, right? So they have to be perfect squares to come out. All right, let's see what's next here. What I want you to do now is turn to page 150. So turn to page 150. We're going to talk about the theorems that are in the book. I'm not going to make you write them down, but we are going to talk about them. So I'm going to do my best to explain what they're saying there. I'm going to read the first one there, linear pair perpendicular theorem. If 2 lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. Read that again. If 2 lines intersect to form a linear pair of congruent angles, then they are perpendicular. So here's a line with another line intersecting. You can see that we have a linear pair that's formed. But the linear pair does not add it adds up to 180, but they are not congruent to each other. So this angle here, let's see, this angle is not congruent to this angle. They are a linear pair, they add up to 180, but they're not congruent to each other. The only time that they can be congruent to each other is if the linear pair that's formed is formed the only time that these two can be congruent, that's what I'm trying to say, sorry about that. The only time that these two angles, this angle can be congruent to this angle, is when this is 90 degrees and this is 90 degrees, because they at the same time have to be congruent and add up to 180. And since they have to add up to 180 and be congruent at the same time makes them 90 degrees, it makes it a right angle, which explains that theorem. If 2 lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. The next one, in a plane, if a transversal is perpendicular to one of 2 parallel lines, then it is perpendicular to the other. We kind of already know this going by what we've learned in the past, just by parallel lines cut by a transversal. It says, this is saying that if one line, if the transversal is perpendicular to one of two parallel lines, those two are parallel, then it's perpendicular to both. We really don't need a theorem for this because we already know if the two lines are parallel and this is a right angle, this is its corresponding angle, it's also right. And if this one is right, this one has to be right, then this one has to be right, and this one has to be right, and on and on and on. So you have 8 90-degree angles. So, I'm sorry, what it's saying is if this is perpendicular and these two lines are parallel, then this is also perpendicular. Okay? Next, in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. Almost seems like the converse. So if two lines are perpendicular to the same line, so if this is going on, if these two are perpendicular, then these two lines must be parallel. It's just kind of going in the opposite direction of the one we just talked about. The reason that I'm telling you about these terms, we don't really use them much, but there's some problems that we're going to talk about, 17 through 22, that you have to think about those theorems in order to answer or you can just kind of think about what you've learned before this section to answer those problems. So let's look at 18 and 20. So number 18 is showing that these two angles are perpendicular. Determine which lines, if any, must be parallel. Explain your reasoning. So if any, what two lines are parallel? This is line A, this is line B, and this is line C. So if these two angles, this again is, I refer back to what I know about perpendicular lines, and I mean not perpendicular, but parallel lines cut by transversal. I think back to the converse of the consecutive interior angles theorem. The converse says that, the consecutive interior angles theorem says that if consecutive interior angles are supplementary, then they're parallel. So you could say that B is parallel to C, and your reason could be either that the converse of the consecutive interior angles are supplementary, or theorem, which states that they're supplementary, or you can use, let's look back on page 150, you can use the lines perpendicular to a transversal theorem. Okay, so that third one there. So you could use either explanation because you're supposed to explain your reasoning. Number 20 has this angle as a right angle and this angle as a right angle. Now they may all look parallel. Well, A and B may look parallel to each other. C and D may look parallel to each other, but that doesn't mean that they are. You can't prove it. It could be off by 1 degree. So what they're asking really is that if these two angles are right angles, does that mean anything's parallel? It looks like it might be because it looks like it is, but here's what's going on in my head. I'm thinking this. Let's see if I can make this happen here. Oops. I'm going to lock these two in because we know for sure. I don't know if I have that locked. Hold on a minute. There it is. I'm going to lock those in because we know for sure that that's a 90-degree angle. And then I'm going to try to lock these in. I'm not going to be able to include the letters, but that's okay. 3. Now, here's my counterexample. They look parallel. They could be parallel, but are they parallel? Well, what if I do this? Those are still perpendicular, but the lines are A and B are not parallel, C and D are not parallel. So there's my counterexample. So there is On number 20, none. What lines are parallel, if any? None. Or, well, yeah, we'll just put none. And then you can explain, whenever there's none, you don't really have to explain it. You could just say that there's not enough information to determine that anything is parallel. Tomorrow, we will go over the proof that I wanted to go over today. We just don't have time for it, especially since I'm not here. So we'll cover this proof, and then you can do the number 15 that I had assigned you, like this one. So your assignment tonight or today, if you have time left in class, is this assignment not including number 15, because that's the proof. So all of them but 15 you should be able to do. Work on that until the bell rings. Bring it in tomorrow to turn in at the beginning of class.